Welcome everyone to another installment of Dave Does Precalc from Home. Today we're talking about section 1.4, complex numbers. So, for most of the semester, I have been telling you that you can't take the square root of a negative number. Every time we get into these situations like square root functions, I'll say that it is a domain restriction. You can only do non-negative numbers in square roots, so 0 and positive numbers, the only things allowed. Today we're going to start talking about imaginary numbers. Which is another addition to the long list of things that have names that I absolutely hate. Imaginary numbers is a terrible name for what we're going to discuss because all numbers are imaginary. But imaginary numbers in this context means square roots of negative numbers. We denote imaginary numbers with the letter I. Lowercase I means the square root of -1. This is sort of like the basic unit of imaginary numbers. We can get bigger imaginary numbers if you're dealing with something like the square root of -4. You can split that into the square root of -1 times 4. And then you can split the square root. So this is the square root of -1 times the square root of 4, which is, this piece right here is I. This piece right here is 2. So we would write this as 2I. That's the square root of -4. If you're dealing with something like the square root of -25, we would call that 5I. Square root of -100, that's 10I. So we're basically taking the square roots of these numbers as if they were regular positive numbers that we could take the square root of. And because they are negative, we are attaching an I to them to indicate that these numbers are imaginary. I guess somehow more imaginary than the rest of numbers. But now is perhaps not the time for me to go on angry rants about naming conventions. So, this is imaginary numbers. Astute viewers will notice that this section is about complex numbers, not imaginary numbers. So what's the difference between a complex number and an imaginary number? I'm glad you asked. That's what I'm going to talk about right now, as soon as I find an eraser. Complex numbers are sums of real numbers and imaginary numbers. Real numbers are the numbers that you're used to. Imaginary numbers are what we just talked about, square roots of negative things. So, if you try to put the two of them together, you end up with what's called a complex number. So like 2 plus 3I. This is a complex number. It has a real part. 2 is real. Has an imaginary part. 3i is imaginary. And if you add them, you get a complex number. Looks like this. Negative 27 minus 13i. This is also a complex number. 128 minus 2i. This is a complex number. Anything that can be written as the form a plus bi. The sound my cat makes when I step on her. Anything that can be written as the form a plus bi is a complex number. She's okay. She's just startled. Like me. Okay, this is complex numbers. This is the generic form of any complex number. So that's what they are. Next we're going to talk about what we're doing with them. So I will again erase all of this. The first thing we're going to do with complex numbers is add and subtract them. Adding and subtracting numbers works pretty much exactly like you would expect it to. If you have something like 3 minus 4i, this is one of your complex numbers, and you want to add 12 plus 7i, this is a complex number, this is a complex number, we are adding them. This behaves exactly like you think. You just combine like terms. For most of this, we can basically pretend that your i's are just x's, and this works exactly like polynomial addition and subtraction. So the 3 and the 12 are like terms. If I'm adding those, I'll get 15. The negative 4 and the 7, the negative 4i and the 7i are like terms. So if you add those, you get 3i. And you're done. That's all there is to it. If you're going to subtract things like 2 plus 8i minus 4 minus 5i. Again, you're still combining like terms, but you got to be careful about distributing this negative sign in there. So this is going to be the same as 2 plus 8i minus, or you could say plus negative 4 plus 5i. Once you distribute that negative sign, 4 becomes negative, 5 becomes positive, and now you're just adding them again. So this will give you negative 2 from these guys and 13 from those guys. Works exactly like you might think. So hopefully there have been no surprises here. Next up, we're going to multiply them. Multiplying these things is pretty much always going to involve FOIL. So if you have something like 2 plus 3i times 7 minus 1i, we'll say, this is a binomial, this is a binomial. Again, if you want to just pretend that these i's are x's and treat this like you're multiplying two polynomial expressions together, it works exactly the same. We just have i's instead of x's, except for one little step at the end. So if these were x's and we were just multiplying these, we would use FOIL. So the first term would be a 14 from these guys. The outside term would be negative 2i from these guys. The inside term would be 21i from these guys. And the last term would be negative 3. I times I will give you an I squared. So now here's where this stuff gets just a tiny bit sneaky. We have to remember what I means. I is the square root of negative 1. So here we have an I squared. I squared is the square root of negative 1 squared, which is negative 1. So this whole thing here, this is 14 minus 2i plus 21i minus 3. I squared is negative 1. So this last piece on the end is actually just plus 3. As a final step for these multiplication problems, we should combine like terms. We have 14 and positive 3 over here, so that'll give me a 17. We have a negative 2i plus 21i, that should give me 19i. This is the final answer. And we should note that when you multiply two complex numbers together, the result is a complex number. If you start with a plus bi and a different looking a plus bi, you should still get something that looks like an a plus bi. All of your answers for this section should look like this. I'm going to do one more of these real quick, and then we'll move on to the exciting stuff. Let's do negative 5 plus 12i times 7 minus 3i. No, let's do plus 3i. There we go. Okay. Again, the process is just FOIL. First term will give you a negative 35. Outside terms will give you negative 15i. Inside terms will give you, I did not plan this. 12 times 7 is 70 plus 14, 84. 84i from the inside term. And then the last term will give us 36i squared. Now, just like before, we have an I squared term here, and we need to do something about it, because our final answer should look like a plus bi. Final answer should not have any I squareds involved anywhere in it. So we have to do something about this I squared. I squared is negative 1, so this whole term is the same as negative 36. So now we can combine like terms. I have a negative 35 and a negative 36. Those will combine into negative 71. And a negative 15 and a positive 84, which completely unintentionally looks like it turns into a 69i. Nice. Without additional comment, I'm going to move on to division. I don't know why I left that 1 there. Multiplication should have been a 2. Division is the third thing we're going to do. Division is honestly the weird one of the group. If we have something like 2 plus 3i is a good starting point. 4 minus I. Let's do this. This is a division problem. And at first, probably does not look very intuitive if we're talking about how to divide by a sum like this, especially or even a difference like this, especially when we're calling this one number. If this is a single complex number, how do you divide by this number when it has two pieces? That's the challenge. And here's the trick. This trick is not very intuitive, but it's a good trick. You take this thing on the bottom, you multiply this fraction, top and bottom, by the conjugate. So the conjugate is the same number, but with the opposite operation here. So if this is 4 minus I, the conjugate is 4 plus I. Conjugates. A plus BI and A minus BI. This is what a conjugate means. You keep the numbers the same. A is still A, B is still B. You just switch the operation from plus to minus. That's called a conjugate, and the reason we're multiplying by the conjugate, I hope, will become very clear in a moment. Ultimately, the goal here is to get a difference of squares situation, where when we multiply this out, stuff is going to cancel. So I'm going to move down here and start multiplying. I'm going to start with the bottom, because that's the really interesting part, and the reason I chose this number to multiply, top and bottom. First, I get a 16. Outside, I get a 4i. Inside, I get negative 4i. And the last will give me a negative I squared. Here's the beauty about multiplying a complex number by its conjugate. This middle terms, both of the terms with an I, are guaranteed to cancel. Plus 4i and minus 4i will cancel each other out. This thing, minus I squared, this is the same as plus 1. So whatever else is happening on top, the bottom of this thing is now just a 17, which is really nice for me. Instead of dividing by a complex number, which has two pieces, after I multiply by the conjugate, now I'm just dividing by a real number that has one piece. And this will always happen every time if you multiply by a conjugate. The power of multiplying a complex number by its conjugate is all of the I pieces will cancel, and you'll just have a real number. So let's look at what happens on top. 4 times 2 is 8. Outside will give me a 2i. Inside will give me a 12i. Last will give me a 3i squared. So this 3i squared is going to turn into a minus 3 on the back end. And then 8 minus 3 should give me a 5. 2i plus 12i should give me a 14i. So, here's the benefit of doing this. By multiplying by a conjugate, I've transformed this thing, which started out as a fraction, into a different looking fraction. The huge difference here is that the bottom is now just a real number. It's not a complex number anymore. It's just a real number. So I can split this term. I can say that this is 5